Determine the area of the region between the curves by integrating over the x-axis or the y-axis. We have x is equal to y to the third plus 2y squared minus 3. That's the first curve. And then the second curve is x equals negative y squared minus 3. So we're looking for the area that is enclosed by those two curves. So we're looking for the amount of area that I'm highlighting here in this aqua blue color. That's the area that we're trying to calculate. Now, because this is with respect to y here, everything's defined in terms of y, and because the shape of the curves and the way that it's set up, it would be much easier to set up the integral so that it's in terms of y rather than x. If we did this with respect to x, we would have to split this up into multiple areas. Where if we did it with respect to y, we only have to do one integral. So we're just looking at the difference between the purple function and the green function. So this is how our rectangles are going to be set up. It's going this way. And we're just going to take those infinite rectangles and add them up. Now, to start looking about how to set this up, the first thing we need to do is identify the intersection points. So we're going from this point here, which is negative 3, 0, to this point right here, which is negative 12, negative 3. In order to find the area between two curves, we need to take the upper curve and subtract the area under the lower curve. If it's hard for you to determine which one is the upper and the lower because it's in a way that we're not really familiar with, we're looking at it with respect to y instead of with respect to x, think about how we would do this if it was with respect to x. If I have, for example, something that looks like this, and I want to find the area that are between this quadratic and this line. So we're trying to find this area here that I just colored in black. So we're going to go from this value of x to this value of x, and we look at our rectangles this way. And then to determine the upper curve, when we're doing it with respect to x, we look to see which one has the largest y values. Now, when we're doing it with respect to y, we're looking to see which one has the larger x values. So looking at it that way, we're going to subtract the green curve from the purple curve. The purple curve is going to be considered the upper curve, and the green is the lower. So we're going to take and find the area under the purple curve and then subtract the area under the green curve. Since we identified our intersection points, we're going to start with the lower limit for y, which is negative 3, and the upper limit for y would be 0. Here is the curve that's purple. It looks kind of like a cubic, but facing in a different direction. And then we have our green curve, which is the sideways parabola. That's this one here. So we're going to take the purple curve, because that's considered the upper curve, minus the green curve. When we try to simplify this to make it easier before we integrate, remember this is a negative here. So when I distribute, these two negatives inside here become positive. So I have y cubed, and then I have 2y squared plus a y squared. That gives me a 3y squared. And then a negative 3 and a positive 3 add to 0, and so the constants drop out. And then we're doing this with respect to y, so I have to make sure I put my dy in here. And then when we integrate, we get that the area is 6.75.